Today we're going to talk about something called the pH scale, which is a way of measuring or comparing how acidic or how basic a substance is. So you've already learned about different theories of acids and bases, and you know what makes an acid, you know what makes a base. So now we need a way of giving a number to a substance to describe, is it acidic, is it a base, but also, if it's acidic, how acidic is it? Because different acids have different strengths. So before we talk about how we measure the acidity or basicity of a substance, I'm going to talk to you about something called dissociation of water. So water, H2O, can be broken down into two ions. It can become H positive plus OH negative, which is a little confusing because you ask yourself, well, is it an acid or is it a base? Because H positive means it's an acid, but OH negative means it's a base. Well, it's neither. Water is neutral. But in any glass or sample of water, you are going to have some amount of hydrogen ions and hydronium ions. So if this here is my glass of water, color it blue. Most of the molecules in the water are H2O. So H2O, you've seen before, it's a covalent compound, which means it has bonds that share electrons. So here's what water normally looks like. But in any sample of water, you are going to have some amount of the ions. And what happens is that this bond gets cut. Both valence electrons go to the oxygen, and that's what makes it have a negative charge and satisfy the octet rule. So this is the ion OH negative. It's a polyatomic ion hydroxide. Hydrogen has given its electron over to the O, so hydrogen has lost an electron while it's hydrogen positive. And here's my base, OH negative. So even though water has some amount of hydrogen and some amount of hydroxide in it, we say it's neutral. It's neither an acid nor a base. And the reason for that is that it's always going to have the same number of hydrogens as it has hydroxide ions. So they balance each other out. But that changes once I add an acid or a base. So for example, right now, here's a glass of water. Most of it is H2O in liquid form, but it will have some hydrogen ions and some hydroxide ions. That said, if I were to pour in some HCl, which is hydrochloric acid, I'd be increasing the number of hydrogen ions. And at that point, the sample would have more hydrogen than hydroxide, and that would make it an acid. So quick review. If the amount of hydroxide, the square brackets I'm using mean concentration of, and that just means how much there is. So if the concentration of hydroxide is equal to the concentration of hydrogen, then we say the substance is neutral, right? It's neither an acid nor a base, because it has the same of both. However, if the concentration of hydrogen is greater than the concentration of hydroxide, that means there's more hydrogen ions than hydroxide ions, such as in my hydrochloric acid example up here, then we say the substance is acidic. Which makes sense because you've learned that hydrogen ions are what make an acid. On the flip side, if a substance has more hydroxide ions than hydrogen ions, then that means it's basic. And we use a scale of measurement called the pH scale to compare substances and describe how acidic are they or how basic are they. So a substance that's neutral, we say has pH of 7. So for example, pure water would be 7. A substance that's acidic is going to have a pH that's less than 7, so the smaller the number, the more acidic. A substance that's basic is going to have a pH of greater than 7. So the greater the pH, the more basic a substance is. And you can see that on the scale down here. 7, pure water, is neutral. As you get into the smaller and smaller and smaller numbers, you get into stronger and stronger acids. As you get into the higher and higher numbers, you get into stronger and stronger bases. Now here's the thing that's really tricky about the pH scale. It's not a linear scale. It's a type of scale that's called logarithmic. And what that means is that each step, from 1 to 2, 2 to 3, so on and so forth, means a change in the amount of hydrogen ions by a factor of 10. And I'll show you what that means. So, if pure water has a pH of 7, and I jump one step down to milk, I'm now at a pH of 6. What that actually means, so I've gone down 1 unit, is that milk is actually 10 times more acidic than water. It's got 10 times more hydrogen ions than water. Bananas are going to be 10 times more acidic than milk. They're going to have 10 times the number of hydrogen ions. Tomatoes are going to be, again, 10 times more acidic, have 10 times the number of hydrogen ions as bananas. What if I asked you how many times more acidic tomatoes are than milk? Well, you went down 10 times, and then you went down 10 times again. It's not 20, it's actually 100, because 10 times 10 equals 100. So let me give you a couple more examples like that. If I asked you to compare bleach and eggs, and I asked you which is more basic, so that means which one is a stronger base, and by how much? Well, let's look them up on the pH scale. Bleach has a pH of 12, and eggs have a pH of 8. So bleach is definitely the stronger base, because the higher number means it's more basic. And if I asked you how many times more basic, well, 12 down to 11 is 10 times more basic. If I went down to 10, that would be times 10 again is 100. Down to 9 means times 10 again is 1,000. And then finally down to 8 times 10, that's 10,000. So 10 times 10 times 10 times 10 equals 10,000. And I have to do 10 times 10 4 times, because 12 minus 8 equals 4. So I've gone down 4 steps on the pH scale, and each step marks a change by a factor of 10. So bleach, even though it's only has a pH that's 4 higher than eggs, is actually 10,000 times more basic. That means 10,000 times of a stronger base than eggs. What that means in sort of on a chemical note is that bleach is going to have 10,000 times more hydroxide ions than eggs. So that's part 1 of this lesson. Part 2 is quite simple. It's talking about indicators. Indicators in chemistry are substances that tell us about whether or not a substance is an acid or a base. So the first set of indicators are indicators that just tell us acid or base. They don't tell us whether or not we're looking at a weak acid, a strong acid, a weak base, a strong base. So in liquid form, the indicator we would use is called phenolphthalein, sort of a funny word to say, phenolphthalein. And if phenolphthalein turns a liquid a pink color, then that means that liquid is a base. If phenolphthalein remains colorless, remains clear in a liquid, then that means that liquid is an acid. And it's right around a pH of 7 that phenolphthalein will change from acid to base. Next is in paper form, something called litmus paper. And litmus paper will turn blue. It's in contact with a base. So I remember base blue because they both start with B. And then it'll turn red when it's next to or comes in contact with an acid. And both end in D, which is how I remember. So these are useful indicators if all I need to know is whether or not a substance is acid or base. And it's really easy to remember what color means what. There are much more complicated indicators if I want to know how acidic a substance is. Now, these aren't that useful if all I want to know is acid or base, because there are just way too many colors to remember. But if what I want to know is I am looking at two acids, which one is stronger, then these are really useful, because you'll see that there are different colors for every single number on the pH scale. So in liquid form, the indicator we use is simply called universal indicator solution. And that's what it's called because it can indicate pretty much any pH. In paper form, we just use something called pH paper. And you'll see the colors are fairly similar. Sort of yellow-green color is neutral. As you go into darker greens and blue, you're getting more and more basic. And as you get into oranges and then deep reds, you're getting more and more acidic. So those are the indicators we use to figure out how acidic or how basic a substance is.